Okay, well, welcome everyone. We're very glad to have Zhen from Penn today talking about measurement prepared for quantum critical states. Thank you very much.
All right, thank you very much for the introduction and for the invitation. It's actually my first time being in this center, and it's very nice. Right, so today I'm going to tell you some story a little bit different than conventional condensed matter settings. So we're going to talk about how to prepare quantum critical states from unitaries and measurement on these quantum simulators. So before going on, I may make the acknowledgement. So this work is done with collaboration with Zhongyang Li and Wenjie Ji and Matthew Fisher from UCSB, and this is the reference. And you can also see a relevant reference here from Ashwin's book. So in conventional condensed matter physics, what we do is to study a set of material. We simplify their crystal structure and then write down a model Hamiltonian. From that model Hamiltonian, we may have some low energy description, which has fields and their derivatives. And by changing some parameters in that setup, we may study different phases and their phase transitions. And so in condensed matter physics, we care about these interesting quantum states organized by these principles. We may be interested in some symmetries of the system. And by the symmetry, we can have ordered states and disordered states. And examples like magnetism and superconductivity. We're also interested in topological properties of the states. And there are many, many new examples coming from that category. We have fraction quantum Hall states being liquids, and they carry fractional charges and statistics. And they have this hallmark of long-range entanglement. And we may also have interest in states which combines these two principles together, symmetry and topology. And topology insulator is just one of these examples that we have. And today's scope is a little bit different than the traditional condensed matter, where you study material and Hamiltonians and so on and so forth. So in recent days, these quantum simulators, which are programmable lattice quantum systems, are more and more popular. And they have more degree freedoms we can manipulate. The platform can be cold atoms, trap ion, or Rydberg atom array, or superconducting qubits. So basically what you can think about is a array of quantum qubits, where by either shining lights or other kind of manipulations, you can do unitary gates across a few qubits, and then read out their states by measuring them. So essentially, we're not thinking about the Hamiltonian, but thinking about some states going through some unitary transformation and doing some measurement, either randomly or by design. So that's the scheme we want to consider. And what can we do with these quantum simulators these days? What is the first thing people think of is to simulate the real quantum Hamiltonians with the quantum simulators that include these hard models, like Bose-Hubbard model, Fermi-Hubbard model, frustrated speed models, and so on and so forth. One can also think about quantum dynamics arises with unitaries and measurement. And basically in that settings, we care about how the entanglement of the states evolve or develop in that system. So you can see.
So the Hamiltonian we're talking about, is that essentially the full unitary I should think of as either the IHT of the H that I'm trying to simulate, or
yeah, so
like there's also some Hamiltonian just for these like Rydberg atoms or whatever, right?
There's also some Hamiltonian.
But that's not the Hamiltonian.
That's more restricted. So what we can think about is each step you can do a unitary, and each of the unitary can be independent from each other, and that's fine. Yeah, so it's slightly more general than the Hamiltonian. So that has also been an exciting directions. People have seen transitions in the entanglement structures by tuning the measurement rate of these hybrid circuits. You can see a review here. So today it will be a slightly different goal. What we want to do is to use this setup of measurement, unitaries plus measurement, to prepare interesting quantum states in particular, how to prepare a critical states using this setup. So the state preparation is really given by this very simple schematics. You start from some trivial states, which in this case is a product state of spins along x directions, and then do some local unitary transformation to build up some local entanglement between the spins, and then do some measurement on subset of the spin, and then look at what's the resulting state. So that's the simple preparation scheme I'm thinking about here, and it could be much more complicated than this, but already this setting already gave you some interesting physics by changing these. So the talk will be in 3 parts. The first part, I just give you some examples where interesting quantum states like symmetry breaking states and topological order states can be achieved by these unitaries plus measurement. And then I'll tell you how to prepare critical states with post measurement using this degree freedom of measurement angle. And so post selection is a big problem in experiments, because if you want to do post selection, you are discarding a lot of the experimental results and only look at a very small subset. So a practical problem is that what will happen if we don't do post selection? We do measurement and we record all the measurement outcome. Do we still have a meaningful kind of critical states after that? Right. So the last part we'll be dealing with the question: if you don't do post selection, what will happen, and is there a way to tell a phase transition from this setup? So yeah, let me start from these very simple examples. They are really not very deep, it's just quantum mechanics. You start from, for example, there's this 1D example of a resource state, which is really a so-called Z2 cross Z2 SPT state. So you start with a spin chain, which has even number of spins with periodic boundary conditions. And then you put on this so-called cluster Hamiltonian, where you have a Z, X, Z on adjacent 3 sets, right? So so each of the term will be commuting with each other, and you will have a ground state that's satisfying all these conditions. And so that will be constraints of the ground state, but also the symmetries, also the ground state will respect these 2 Z2 symmetries, which are spin flips on even and odd sets. So this state can be generated by a product state by a finite depth unitary. You do a CZ, so a control Z. It's not very important. It's a finite depth unitary that you can start to generate these states. So now let's see if we can do something interesting to that state. So we can actually prepare this so-called GHD state, which is essentially a symmetry breaking state in these one-dimensional settings. So the essential thing we want to do is to measure the x component of the spins on the even sets. So if you look at these constraints, if you measure an x operator on the even sides, then it gives you a new constraint, which is the 2 z's on the odd sides on the neighborings will be equal to 1. So that gives you Ising constraints on the remaining spins, right? And you also have this constraint of symmetries that's not affected by your measurement. So if you only measurement along x direction, then you have these 2 new constraints. One is the system must be obeying the Ising configurations, and also it will be a symmetric state. And it turns out with these 2 conditions, the only state that's possible is the GHC.
Is this somehow like a mixture of a smooth and rough boundary of like a Tor code in some sense?
Smooth and
rough, like a mixture, because like the product of sigma x constraint would be kind of the rough boundary constraint.
I'm not sure. So the boundary of that Tor code, you can think them as Ising model itself. Yeah. But here we have 2 global Z2 symmetries.
Yeah. Right. So basically, I was just asking, like, if it's like a combination of 2 different boundaries.
I don't know.
Because it's
so it could be the symmetry breaking boundary condition, but in a symmetric sector. Mm-hmm. if that's helping.
I was wondering if you're post selecting on +1s for all the even ones, wouldn't it be like exponentially small?
Right, so that's the problem of post-selection, which we are postponing to the third part
Okay.
of the talk. Yeah. So here is the most simple setup where we do post-selection and select the state we want, and that's the state which is the symmetry breaking order. Right. And we'll talk about what happens if we have disorder. We have random outcome in the end. So that's a one-dimensional example, and this one-dimensional example is very illuminating. You can generalize this story into 2 dimensions by going by doing similar things. So you can design a so-called cluster states, which is this resource state on a leaf lattice where you have sites and the links, and the sites will obey this star operator as its constraint, and the links will obey this ZXZ as well. And in this setup, you can define 2 Z2 symmetries. One is a zero form Z2 symmetry, which is flipping all the spins on the sites. And you can also define a 1 form symmetry, which is flipping the spins along a closed loop on the dual lattice. So this Hamiltonian will be respecting these 2 symmetries. And what we can, so the first thing we can do is to measure axis on the edges. And then that will destroy these star constraints, but you'll leave the constraint to be the Ising configurations on the sites, right? So in that situation, you will realize a symmetry breaking order on the sites by doing these X measurements. And you can also do, so because there are 2 sets of degree freedoms, there are links and edges. By measuring the sites, by measuring edges, you are stabilizing a Ising ground state of the spins on the vortex. By measuring the vortex, you can actually stabilize a toric state. So by measuring X operator in the center, you're essentially having a constraint that for Z's product to be 1. And because this symmetry is intact, you will always have this loop operator of X equals 1. So you will generate a toric ground state by doing a measurement on the vortex. So you see this starting from the resource state and then measure partial of the degree freedom really give you the ability to prepare different kind of states, symmetry breaking or topological order. You can view the topological order as a new form of symmetry breaking as well. So just some remark. By doing unitary class measurement, you can actually prepare state that are not reachable within just the unitary itself, because we know toric code is not reachable by using finite depth unitaries. And so this trick of doing a clustered state and then measure half of the spin is equivalent in some sense to this Cramer's linear duality. As you can see, it maps to the other states on one side to the disordered states on the other side. And recently, so because Cramer's linear can be think about as some kind of generalized gauging procedure. So there are new developments, some non-abelian topological order can also be achieved by using this generalized idea of measurement equal to gauging. And you can achieve a lot of non-abelian topological order also using unitary class measurement in this scheme. So that's the motivating examples, and what we want to do is to see if we can drive some transitions by starting
Sorry, just a question about
yes.
what you mentioned about measurement being equal to gauging. Do I would it be right to sort of think of it as the projector that you're using kind of acting as a Gauss law constraint on the states,
Yeah.
or?
I think so. Yeah.
So that's all there is to this?
So it's equivalent to this Cramer's linear duality. So that's somehow it's like a gauging.
I see.
The reason I'm interested in sort of finite depth circuits is because that will not change sort of the entanglement structure, whether like area law or these type of things. Is that the reason?
No, so
Just the limits the phases.
I'm just making the comment is that, you know, usually when we study quantum physics of matter, we just use the definition that if they are connected by finite depth unitaries, then they are the same phase. So now there's a new set of rules, which is to be developed. Is that if you start from unitaries and measurement, you may have a coarser sense of what phases are equivalent, what phases are reachable by these schemes. Right.
So for instance, do you mean that you consider theories that differ by discrete gauging to be the same because of that?
Yes. Yeah. By this set of rules, we may consider Curry code and trivial states are the same because they are. It's a point of how do we define the rule of games? Right? So if we define the rule of game is only through unitaries, then they are different. But if we define the rule is that we allow to do measurements, then they could be the same.
What's an example of two things that are distinct under these rules?
That's a very good question. I don't think there's a clear answer in this regard, but there are some examples which I'm not familiar with.
Fibonacci properties are not like Fibonacci might be.
Sure.
Yeah, I'm not sure what's the examples. Yeah,
So it could be, for instance, that everything gap is related to everything else.
it could be, but I think at least there are example people claim to be distinct from the trivial phase.
What's the basis for the claim that it's distinct?
Uh,
Like, is there something you compute that you think is an invariance or something?
Like the non-solvable groups as an example, where you can't prepare it by sequence of defined depth circuit. Like doubles of non-solvable groups. Also like Fibonacci.
Yes, you could look at the width class, right? Like if they're distinct, probably you can't find some sequence.
I mean, if a naive thought is that if two topological order are not connected by discrete gauging, then they may be in different class. But that may be too restricted to this simple rule.
There would have to be abelian gauging, is that what you're like, that's
Yeah.
somehow what elements.
Are you using a Abelian gauging or
Abelian, yes.
Okay.
That at least in these examples are Abelian.
I guess like, yeah, measurement would be Abelian gauging. I don't know what.
I don't know a version of
Non-Abelian gauging.
rule and non-Abelian, yes.
But it's still a projector, right? Like the non-abelian gauging is still a projection operator. So why is that not a measurement?
Well, I guess here the measurement, I mean, the gauging is really like the finite depth circuit that does the minimal coupling. And then the measurement does the basically integrating out the matter.
I thought, like, is it in general a measurement just any projection operator?
Yeah, so you could prepare any non-abelian topological orders by measuring all the projectors as well.
Yeah.
But I think then you can't prepare the ground state, for example, of a non-abelian topological order. Because you can't do the here in a abelian case, you can always, when you have errors, you can apply a string operator to like feedback to correct the errors. And in those cases, there's no efficient way to do that. So you can always measure all the projectors, but like you can't fix the errors. I don't know if,
Maybe we'll talk more later.
Yeah.
Thank you for the question. Yeah, so in the following, I'm just giving you some simple kind of story where you can drive a transition for these symmetry breaking states by changing what your measurement scheme is. Essentially by changing the measurement angle between two different directions. Sorry. All right, so we can, in order to drive a phase transition, we usually have two phases to think about, and we can think about the trivial limit of the measurement. So before we are measuring all the spins along x direction, which give you these symmetry breaking states, but then we can reconsider these 1D cluster states by measuring the even sites, but along the z direction. If we do that, then we will have from this constraint, we'll have all the x set, all the x direction, sorry, all the spin is pointing along x direction in the remaining degree of freedom. So by measuring the z operators on the even sites, you are actually fixing the configuration of the remaining spins, and that just gives you a trivial state, which is a symmetric product state. So we already find two limits where measuring along x give you the symmetry breaking, and measuring along z will give you the symmetric state. So the question is just what if we measure an angle that's in the intermediate between these two limits, so we can take a closer look of this phenomenon by going to this decorated domain wall picture, which is one of the good pictures for SPT wave functions. So decorated domain wall for the cluster states just in one dimension just goes like this. Because these constraints, it means the domain wall of the outside is bounded with an x charge of the even sites. Right? So that means if you have no domain walls, then you will have an x plus 1 in the middle. If you have a domain wall, then the x is equal to minus. Right? In this basis, it's very easy to see. If we measure the x direction of the operator, we are fixing a domain wall configuration, and essentially we're just picking one component of this huge wave function, and that one component has all the domain wall configuration fixed. Right, so that corresponds to, you can think of them as a zero compression limit of classical Ising model. And if we measure the z operator along the even sites, then that means we want to fluctuate the domain wall, fluctuating the domain wall on the outsides, right? Because we are not measuring precisely x, we're measuring z. So all these configurations will be there in the resulting wave function. So that will be corresponding to a high temperature limit of a classical Ising model considered on the outsides, on the renewing sites. So that actually can be made very precise. You can work out what's the, you can analytically work out what is the projected wave function. And indeed, it could be written as a superposition of all the configurations, but with a weight. And that weight can be mapped to the Boltzmann weight of a classical Ising model. And that weight, the temperature of that weight is related to the measurement angle by this simple relation. So from that, we get a lot of intuitions what can happen, because in one dimension, we know there is no finite temperature transition for 1 plus 0D classical Ising model. And that means for any small angle theta, you will always have an exponentially decayed correlation function. And that correlation function is controlled by theta measurement angle. But situation could be different in higher dimensions. So in 2 dimension, if we measure the edges, which give you the Ising model on the vertex, then you will have a finite temperature transition, and that gives you the transition when you tune the angle theta, you'll find the transition between the ferromagnetic phase and paramagnetic phase. And if you measure the vertex, what you get is essentially a classical Ising gauge theory. So you have the vertex term, but you don't have the flux term. And the classical Ising model at finite temperature doesn't have any transition. In that sense, the one-form symmetry is restored at any value of theta away from 0. So that tells you the preparation of the toric code is unstable if you move away from the ideal limit, but the preparation for GC state in 2 dimensions is stable if you measure it away from the theta equal to 0 limit. You will still get a symmetry breaking state. So this is reiterates what I'm saying. So we can find what is the critical measurement angle. And if you measure the correlation functions in this 2-dimensional space, you find that that correlation function is just given by the 2-dimensional Ising CFT because the partition weight is just the 2-dimensional Ising model at critical point. So it's kind of an interesting correspondence. Here is the wave function, the amplitude of the wave function is mapped to a Boltzmann weight of a 2D classical Ising model. So it gives you some kind of all right. And this story actually can be generalized into higher dimension as well. As you can see, we can do a 3-dimensional cluster state by setting up this lead lattice in 3 dimensions. In that case, we'll have 2 symmetries, 0-form Z2 symmetries, which are acting on the vertex, and 2-form symmetries, which are acting on the links. Right. So in that case, there will be no transition if we measure the vertex, because we know classical 2-form Ising gauge theory also have no transition at finite temperature. But classical Ising theory, if you measure the edges, it becomes the 3-dimensional classical Ising model, which has a finite temperature transition, which maps to the finite angle transition. And in 3-dimensional, we can also do some different forms for cluster states. So here we have, I think it's face-centered cubic lattice, and we can define vertex operators and face operators. So this is a 3-dimensional cluster states which has both 2 1-form symmetry of Z2 type. And in that case, when you measure, say, the X operators on the links, you will find a 3-dimensional Ising gauge theory. And that has a finite temperature transition, which means the preparation of 3-dimensional gauge theory is stable at certain angle.
On this angle, are you able to calculate it analytically, or is it?
Yeah, everything is analytic here. Well, no. So for this one, it's not, because for this one, we know the Ising model in 2D has exact
Higher dimensional.
higher dimension is, yeah, it's equivalent to say, you cannot solve Ising model exactly in higher dimension. All right, so this is just a summary for the first part. So what we're doing is start from this trivial state and do the cluster entangler, and then measure half of the spins and look at the remaining states. Right? And it turns out by measuring different angle, it is equivalent to start from the Ising model and then do imaginary time evolution, and the imaginary time is controlled. Sorry. It's evolved by this, and the beta is controlled by your measurement angle. And so you have these kind of phase diagrams, which tells you the stabilities of these different preparation schemes, whether they are stable or whether they're not. And you can study phase transition in these settings, and that will give you, in this particular scheme, give you some classical Ising model or classical Ising gauge theory at finite temperature.
So as you dial the theta, do you actually see like power law decay of correlation functions?
Yes, so in this case, you'll see the ZZ correlation. It's the same as the Ising model in 2 dimensions. All right, so that's the simpler part, because we assume post-selection, and when we assume post-selection, everything seems very simple. You just get the unique state in the end, and we can analyze their properties very easily. Everything can be done analytically because we start from an exactly solvable point of the cluster state. So the tricky part is what we do with no post-selection. In that case, we have random outcome, and these random outcomes. So when we have random outcomes on the links, then we get a mixed density matrix where they are weighted by the probability of certain outcome come out, and that's the wave function corresponding to that. So the question is that if we do this no post-selection, recording the result of the measurement, is there any structure in this mixed density matrix we can tease out, or is it totally just random and you cannot do anything about it? And to do that, let's look at a specific outcome, which is labeled by S, which is the measurement outcome of the link variable. And if we do that, we can for that specific outcome, it's still a exactly solvable model, and we can map that wave function. And it turns out that wave function with that specific outcome is also similar to the classical Ising model. The wave function weight is proportional to a Boltzmann weight of a classical Ising model. The only difference is that, the bound variable is controlled by your measurement outcome. So you will have a random bound Ising model. You would think that you have a random bound Ising model in each of the configurations when you measure it. And in the two-dimensional random bound Ising model, people know this is the classic phase diagram. So if you have a random bound Ising model, each bound is independent of each other. And we assume the bound which appears, so x is a plus minus one variable, and is chosen randomly through a probability distribution. P minus is the probability of having a minus bound appear in this Hamiltonian. So you have a phase diagram in terms of temperature and this probability of P minus. At zero probability of minus bound, you just have the ferromagnetic phase, and that has a finite temperature transition. And when you tune the minus bound probability, you'll get to a spin glass phase at a high probability. And then there is a transition between the ferromagnetic phase and paramagnetic phase. And interesting, there is an exactly solvable point, exactly solvable line in this model, which is called a Nishimori line, and that encompasses this exact solvable multi-critical point. So our model is also kind of, if you look at each of the individual configuration, it's also kind of random bound Ising model. So the question is, can we explore the phase diagram of the random bound Ising model by doing this measurement? Question.
Could you explain a bit about the phase transition between the paramagnet and the spin glass and the ferromagnet and the spin glass?
So I don't think there's a phase transition here. So this line is drawn in there. It's not a phase boundary. The only phase boundary is between the red region and the white region. This line is the exact solvable line by some structure.
Does this line coincide with our G flow or not?
Yes, I think so. So these are right. So these lines will be stable, but will flow along this direction and along that direction.
So there are two different, the transition from the ferromagnet to the paramagnet, there's two different
There's two
behaviors,
classes.
two different classes.
Yeah. Wonderful. So our model is very close to this random bound Ising model, but there's actually a tricky part here, which took us some time to figure out. But in hindsight, it should be very obvious. So the problem is that when we consider the measurement problem, there's always a correlation between the outcome of these spins, because we started from a cluster state which has this constraint. If let's think about theta equal to 0 limit, then when we measure the x along a loop, it's always product to be 1. So that means that the s are not independent from each other. Remember, s is the bound variable after we map to the classical Ising model, and this phase diagram is for the cases where the bounds are independent from each other. But this seems to be a tension here because all the s's are controlled somehow because of these constraints you started with. So that seems to be a problem. You have a correlation between the random things, and this will be the same if you consider a general measurement angle. You can calculate what's the expectation value of that loop operator, and that expectation value actually also depend on theta. So when theta goes to 0, this is E1, but when theta is smaller than 0, this can give you some average value which is controlled by theta. So, but then the thing is to realize that there is actually a gauge degree freedom. So for example, in the theta equal to 0 case, you have random outcome of S, but they obey this condition. And that condition is so-called frustration-free condition. That means that what you can do is to do a gauge transformation on each side to a new variable. So z goes to z tilde by t, and s goes to s tilde by multiplying two t's on their edges. And then you can turn this seemingly random Ising model into a ferromagnetic Ising model. Right. So theta equals 0 is the limit, actually is frustration free. So you have a model that is ferromagnetic in disguise, right? So although it looks random, but it actually is not random. And by doing this gauge transformation, you can brought the system back to the ferromagnetic phase. So similar things happens here. So the theta angle actually controls the level of frustration in your random bound Ising model. And actually, for generic theta, you can gauge transform these correlated randomness into independent randomness. So what we can prove is actually when you have this correlated randomness, we can start from a random bound Ising model and do a gauge symmetrized version. So we can multiply this random bound Ising model by gauge transformation and then sum over all the gauge orbits. And in the end, what we find is that summing over all the gauge orbits give you actually the correlated randomness that we obtain naturally by measurement. The random bound Ising model is given by this, and you do this summation, you actually find this. Another way to see this is that if you just calculate the gauge invariant quantity, which are the expectation values of the loop variables, you'll find that both the random bound Ising model and the correlated randomness give you the same configuration, same expectation value. And the loop variables are so huge, so you can expand every different kind of loop configurations, and that uniquely determine the gauge invariant configurations of randomness. So this is just to say that, although we have this correlated randomness, it is gauge equivalent to a random bound Ising model. And the procedure you want to do is to do this symmetric gauge, start from the random bound Ising model and do gauge transformation, and you'll find that will be related to this correlated randomness that we get in the measurement. All right. So in this phase diagram, what we'll see is that the theta angle controls two things. The theta angle controls the temperature, because in this classical mapping, this beta is still controlled by, so tangent beta is controlled by cosine theta. And another thing is controlled by this theta angle of the measurement is the frustration. As we can see, the expectation value of the loop is controlled by theta. So if we have if the product for S, which is the measurement outcome, is +1, then that means there's no fluxes of your bound configurations. So it's frustration free. But if you have any bound variables, then that will give you a different expectation value, a smaller expectation value. And that means there are fluxes, random fluxes in that Ising configurations. Right. So the angle theta controls two things. The first thing is the temperature, and the second thing is the frustration level, which is equivalently corresponding to the weight of the minus bound appear in the random bound Ising model. Right. So we can only, so by tuning theta, what we can do is only swipe part of the phase diagram instead of the whole phase diagram. We can only swipe part of it because we only have one parameter, and that controls both P minus and beta. Right. And the surprising thing we found is that, well, maybe not that surprising because it's exactly solvable, is that these conditions, P minus and the temperature, which is inverse of the tangent H of cosine theta, they exactly fall on the line of this Nishimori line, which is the exactly solvable line in the random bound Ising model. Right. So that means that by tuning theta, the ensemble is essentially exploring this line in this phase diagrams.
Actually, can I ask a question about that? Like, So in the random bond Ising model, I assume the way you think about it is that you pick some, see what's the statement? You pick some disorder realization,
Right.
and then you have some free energy or something associated with that. And then you average over different disorder realizations. But is that really equivalent to what's happening in your system? In other words, I'm just a little confused. Are you? I guess I think what's confusing me is, are you, because if you were to really do a measurement on your physical system, would the average be taking place would you be averaging the free energy, or would you be, I don't know what how to describe the other one, but where you actually, would you really be averaging the free energy? Is that the relevant thing to
No,
your
we're
setup?
not averaging free energy. So we can imagine measuring some correlation functions. And measuring in different configurations eventually give you just the disorder average correlation function. So we have no analog of free energy.
Yeah, it's not so much the free energy, I guess I'm asking about. I think I'm just trying to distinguish between two different systems. One where you sum over, like where the disorder is another random variable that's summed over, that's
Yes.
totally on the same footing as, you know, the spins on each site. That's one setup, and another setup is where you treat it differently, where you fix a situation for the disorder, and then you have some ensemble for the other degrees of freedom, and then average over the disorder. I'm trying to distinguish between those two cases, and I know that this phase diagram is clearly the latter case. I
Yes,
just wanted
yes.
to make sure that I guess I'm just asking, is your setup also that case as opposed to the first case?
Right, so what we're considering is let's first measure the bonds which fix a disorder configurations and then study that state.
Yes.
And then when we do many experiment, that is equivalent to say each time we fix a bound configuration and study.
But I guess if you're not doing post-selection, I guess I'm saying one option is like for each fixed outcome.
Yes,
for the
you cannot
disorder.
use it too much, right? You can only use it once when we measure correlation function. That's the problem, I guess.
Well, I guess I'm asking you, if you were doing this experiment, would you just repeat it 1,000 times and average over 1,000 times, or would you try to get each ensemble 1,000 times, do the average, like get each disorder realization 1,000 times, do the average for each disorder realization, and then?
Yes, I think that's the way to do it. It's you get the same. Well, I'm gonna tell you a slightly more efficient way to use those configurations, but then that's what you should do. You should naively what you should do is to get the same configuration of measurement outcome, and then that give you the same wave function, and then you measure the correlation function within that set, and then average over different measurement outcome. That give you this random bound. That give you the ensemble average of the. Right. Yeah. So if you start from this. So each time you get the measurement outcome, you get wave function, and when you want to measure correlation function within that wave function, you also have to do a lot of experiments. Right. So, right. So what I'm saying is that the tuning the measurement angle is swiping through these Nishimori lines in this two-dimensional random bound Ising model, which give you the exact solvability of the model. So to determine the ferromagnetic order or the antiferromagnetic or the paramagnetic order, what you should do is to calculate this disorder averaged correlation function, which is this summed over all the random bound with this Boltzmann weight, and then calculate this correlation function within that disorder configurations, and then sum over the disorder configuration. That gets you the definition of the ferromagnetic susceptibility. And the tricky part in our situation is that because we are in this slightly weird gauge where we have this correlated randomness, and this correlated randomness is sum over all the gauge orbits, right? So that's the that's the tricky part, because we are summing over all the gauge orbits. And then this quantity actually strictly give you 0 if you just calculate it. So, but we know there's a hidden order that's on that line. You have a ferromagnetic phase and an anti-ferromagnetic phase. And this hidden order is most significant if we just thinking about the theta equals 0 case. Now we know in the theta equals 0 case, although the S appear random, but you can gauge fix it to a ferromagnetic phase, which has order, right? So what we can do is to do some post editing, which is manually fix the gauge back to the independent random variables, conditioned on the same flux configuration, because the flux configurations are the gauge invariant information in that disorder configurations. So what we can do is to do this decoding after we do a set of measurement. So we do a round of measurement, as Michael said, we get the outcome from the bounds, but we can also get all the vertex spins, maybe the sigma z's. And then the next step is use this configuration to the maximum you can. And how to do that is to, let's say, we have the gauge invariant quantities, which are the configurations of the frustration of this random bound Ising model, which is the flux configurations, and that's gauge invariant, and you shouldn't change that. But what we can do is to start stochastically sample a different set of S's, right? A different set of the bound variable, such that it gives you this two-dimensional random bound distribution. Condition on that, they give you the same flux configuration. So in that situation, although we have only done one round of measurement, we can do a sampling of different flux, different bound configuration given the same flux configuration, and that gives you some. We can calculate that correlation function multiplied by this gauge transformation. So this will be a gauge invariant quantity, and it maximally use one round of measurements that you have. And then you can repeat this, right? You can repeat this experiment, measure outcome of bound and measure the outcome of spins, and then sum of all of them together. So this is a slightly better method because we have used one measurement outcome to its best extent. And the result is the same susceptibility in the two-dimensional random bound Ising model, because we have just fixed the gauge to match the distribution of the random bound Ising model. Right. So in fact, if you just want to know whether there is a ferromagnetic order tendency or there is no ferromagnetism, what we can skip the stochastic sampling. We just keep a minimal cut of negative bounds, right? So say if you have flux configuration like this, we just select a minimal path, which is giving you the same flux configurations, and that's the minimal configurations of negative bounds, and then we calculate correlation functions within that wave function. So that will enhance the probability of having a ferromagnetic order, and this can be done quite efficiently, and you'll see you get some kind of transition as a function of theta by doing this numerical experiment many times. So this may be for different sample sizes, like 1,000 times of running to get this ferromagnetic order and the paramagnetic order. So what I'm saying is that there is some hidden structure here, because our model is not in the precise gauge of the random bound Ising model. The random bound Ising model is in some gauge, and the measurement is actually in a different gauge, which is gauge equivalent. And the quantities you calculate in this ferromagnetic susceptibility in random bound Ising model is no longer viable. And but we can tease out this hidden order in this system by doing some post editing, which is this decoding procedure where you manually change the gauge. After you measure everything, you manually change the gauge into the gauge that gave you this ferromagnetic order. And then you can understand there's ferromagnetic phase and and paramagnetic phase. Question?
Why? Could you have measured something like heat capacity, which seems gauge invariant to?
That's so that's the thing. We're not in a extra material where you have heat and everything. We're just doing many rounds of measurement and trying to determine whether that ensemble has a ferromagnetic order or that ensemble is in the paramagnetic order. So we only have states. We don't have tuning parameters like temperatures and so on and so forth.
You still have the theta to, like changing the theta is like changing the temperature.
It's
So
like
you
changing the temperature.
measure the difference in ensemble as a function of the angles, right?
Yes,
So
yes.
you could do like del rho or del theta.
Right. So if you look at these quantities, which is the yeah, so this is the second order derivative, I guess. No, so this is the fluctuation, and that will have divergence when you go across the critical theta. Right.
Is there some self-averaging quantity that you can potentially find in this model that wouldn't require you to calculate over multiple instances or?
Self-averaging quantity. I think what we can do is to measure sigma z at different positions, and then you average over the whole system. That gives you another level of averaging. But that's usually when people say self-averaging, you're just averaging the same configuration, but calculating correlation function.
In the sense that just to sort of work around this need to kind of redo the experiment multiple times, get multiple instances out of it.
Mhm.
So like if there's some quantity that is analytically known to be self-averaging, then you can sort of extract it from a much smaller number of samples.
Yeah, I think practically you want to just average the ZZ correlation over the same disorder configurations by taking the ZZ, by translating the ZZ operators.
Gotcha.
Through the whole system. All right, so that's the last part. So with without post selection, what we essentially get is a random bound Ising model, but in a hidden way, where you have this weird correlated randomness. And you know, this last part is just tell you can find clever ways to recover the order by doing some classical editing after you measure the state. So I think that's all I want to talk about. So yeah, so now what we can do is to slide over these Nishimori lines along this two-dimensional random bound Ising model. In three-dimensional, similar things happens. You can slide around these lines in three-dimensional random bound or random plaquette Ising model. If we want to explore the bigger region of these random bound Ising model, what we might do is to do some post-selection. So do no post-selection give you this line, and if you do some post-selection, say selecting more ferromagnetic tendency, then you may have another degree of freedom that's going around these points. So that could give you a different universality class here or here, but that will go away from this exact solvable limit, which I can only do it numerically. And another question when we ask is what we go away from this exact solvable limit from the start, right? So we start from these cluster states, which has this exact decorated domain wall wave functions, and if we add some perturbation to that wave function, what will that be an effect of the resulting measurement wave function? So that has to be answered, I think, numerically, and that will give you the indication whether these transitions between different states will be a universal thing or it's just so that we haven't worked out yet. And I think that there's this overall kind of goal is that if you are given a mixed density matrix, either by measurement or other kind of decoherence or disorder, can we distinguish that ensemble of states in some sense, right? So it can be, so in this case, it's defining other states aside from these other states. But we can also ask the parallel question: if you have a mixed ensemble, can we define a topological phase for a mixed ensemble apart from a trivial phase, right? And that will be interesting questions along these lines. It's just to classify phases of matter instead of a pure wave function, but consider a mixed ensemble. This talk is only an example where you can distinguish the disordered phase and the ordered phase in the mixed ensemble by doing these manipulations. And I think that's all I want to talk about. Thank you very much.
So I think this may be related to my question. If you didn't do decoding, if you just ignored the bond variables and tried to just do some measurement on the sites, would you be able to see anything, or?
You don't see anything. Yeah, so because eventually you sum over all the gauge configurations and the operators you measure, the ZZ correlation are actually not gauge invariant. So it will strictly sum to 0. That's why we have to do the decoding in the end. Right.
So right now, do I understand you're doing the same measurement at every site, right? Yes. What happens if you, for example, let data depend on the site? You could have.
That's very good question. Then you have, I would imagine, you have random temperature, then you also have random level of frustration. So yeah, I don't know how to solve that model.
Can I ask, in terms of like classification of phases in mixed ensembles, like, is there a sense in which this post-processing, like if I think of like giving a generic density, like mixed density state matrix, mixed state density matrix, like does that amount to some kind of doing a nonlinear function? Like,
yes, I think it amounts to do some nonlinear function on the state. So each time you have a state that you measure, and then you do some. Yeah, so it's certainly nonlinear. You're doing some operation on that state to transform into a proper gauge configuration. And yeah, I don't even know how to write down that as an operation. Is only an algorithm, but you are certainly doing something to that state. And in the end, the quantity you're calculating is not a linear quantity in terms of the density matrix.
Okay, can I ask, is it obvious that this strategy will necessarily like require smaller number of samples, like, or if you actually want to measure this compared to like the naive like post selection?
I am not exactly sure because I don't know the scaling, but
right.
By intuition, what we are doing is just given one measurement outcome, you are maximally using that measurement outcome many times. So that gives you some speed up in this long procedure of measuring the correlation function. So that's all I can say. I don't know precisely what's the factor that you divided by these procedures. Yeah.
Sorry, can I ask another question? Like because I'm still a bit confused of like if you're not doing post selection and you just do, I guess, kind of post processing or post editing.
Yeah.
Like, is there some aspect of the state that one would not be able to detect using this scheme, or like, is there something missing during this process, or like, would you say, like, I guess you do see like this transition, which is really nice, but like during this, like, is there a distinction still between like doing post selection and use this?
Yeah, so if you don't do this editing, and then you just average over the density matrix, you find the ZZ correlation is strictly 0 because this ZZ correlation is not a gauge invariant quantity. And in the language you are using, this probability distribution is sum over all the gauge configurations, which just project the ZZ correlation to 0 in the end. But when you do this post editing, you are fixing to the random bound Ising model gauge. And in that case, you get the finite number of these equations.
So if there's no more questions right now, thank the speaker one more time.